This is Chelsea Sizemore, Lab MO7, and this is my extra credit. So I went to a lecture with Baseball and Physics by Alan M. Nathan. It was on April 4th. The topics covered were the dynamics of the bat-ball collision, how it works, the wood versus aluminum, and the flight of the baseball, including drag. For the bat and the ball transferring momentum. Force is large, the time is short, so it's like the collisions we learned in Chapter 10. It depends on three things: the pitch speed, the bat speed, and the weight of the bat, and the collision efficiency, or the bounciness of the ball. The velocity of the bat matters more than the velocity of the pitch. And for an example, each miles per hour of the bat speed is worth 6 feet, while each miles per hour of pitch speed is worth only 1 foot. The heavier barrel have higher collisions, but a con to that is it is obviously heavier. However, the bounciness of the collision will cancel out. The pro to making the barrel light is it's more rapid and easier movement, but the con is it's not as high a collision rate as a heavier barrel. The bounciness of the ball for baseball is about 1/2 for the baseball and 1/4 of the initial height. 3/4 of the energy is lost. There are 2 nodes on a bat, and nodes are the fixed points that do not vibrate on the bat. As you can see in the picture, the first node is about 6 inches down from the top of the bat, and the second node is further down. The sweet spot is in between the 2 nodes. Wherever you hit the ball depends on the nodes. If you hit outside of the nodes, the bat will break towards the pitcher if it's hit hard enough. If you hit it too hard inside of the nodes, like closer to your grip, the bat will break towards the catcher. As you can see in this picture, the girl is hitting outside the nodes, so it's breaking towards the pitcher, and the ball is hitting inside of the nodes, so it's breaking towards the catcher. Grip doesn't matter from baseball, and here are some videos of examples why. The grip doesn't matter. As you can see in one of his lectures, he shows a great video explaining why. Watch the bat. As you can see, if the collision starts at the bottom of the bat vibrates, but the top does not move. It has a delay. So in a split second, when the ball is hitting the bat, the grip, there is a way, it is possible to let go for an instantaneous moment and still hit the ball with the same force and direction as if you were still holding the bat. Here's an example of that it really does work by Todd Frazier. As you can see right here, both of his hands are not on the bat, yet the ball is he still hit the ball, and he ended up getting a home run. He completely let go of the bat. It's just proving the point that it is very possible that the grip does not matter. The next part is aluminum versus wood bat. Aluminum has our hollow barrel. It has a faster ball speed, the trampoline effect is better, it won't break, and it can be swung faster. With the wood barrel, it's not hollow, and it will break. As you can tell in this graph, the wooden bat does not hit as far as either of the metal bats represented by the blue and purple line. The trampoline effect, which is a crucial point in why the aluminum bat is better than the wood bat, is the bouncing back of the baseball off of a club or aluminum baseball bat. The reason why is the hard surface, or the wooden bat, the energy went into compressing the ball, rather than in an aluminum bat, energy goes into the bat and the ball. So in the aluminum bat, the barrel is compressed instead of the baseball, which results in the ball losing less energy and being able to travel farther. Also, the bat is redirecting the energy in the ball and is transferring stored energy from the barrel to the ball. In the picture, you can see that the wooden bat, the baseball, you can see the energy is going into compressing the baseball, and in the aluminum bat, the energy is going into compressing the actual bat. The next thing, the last part, is the baseball trajectories. The graph shown at the top is with drag and without drag, and it definitely shows that drag has a huge impact on how far the baseball will travel. So obviously the drag slows the ball down. The ball loses about 10% of its speed during the flight between the pitcher and the catcher. Another thing that influences baseball trajectories is the magnus, or the curve of the ball, and gravity deflect of the ball from a straight line. The drag and magnus forces are proportional to the density in air. In the picture below, it shows how the magnus and the velocity and how it spins, it will affect the flight of the ball. As you can see, a baseball thrown with backspin or an overhand fastball has an upward magnus force opposing gravity, so that a typical fastball does not drop as much as if it were solely under the influence of gravity. On the other hand, an overhand curveball has topspin, so that the magnus force is down in the same direction as gravity, so a pitch will drop more than it would from gravity alone. And also, one really important thing is that the seams do matter, and it affects it a lot, just from this magnus and the wind and everything that comes with it. So that's it for the baseball and physics. Hope you enjoyed it.